So I posted lab 4 today. So we extended lab 3 until the 27th. Sorry, until actually it was till today rather. The original due date was the 27th, and we extended it till today. Did you guys get the email for that? And yeah, I talked to you about it last week, right? And you did your demo, right? For lab 3. Okay, and then lab 4 is the last lab, so we'll have basically the rest of the semester to do that. So that's due on the 25th of April. And this is a new lab. And so it's a little experimental. But the idea is that we have these motors, these DC motors, and the motors have encoders built into them. An encoder is a sensor that tells you either the position of the motor or the speed. And the idea is that we want to be able to control these motors to be able to have them spin at a given RPM value. That would be the set point. And I had one of the guys in my lab designed and 3D printed this enclosure, so it kind of looks like a clock, with the second hand. And so it'll make it easy to see what the motor is doing, because the second hand will be turning. So there's a lot of details here. I tried to put everything I could in this lab description. It's kind of lengthy though, it's 10 pages. So the objective of the lab is to write NEOS 2 software and then build the necessary hardware to implement a closed loop controller to control the rotational speed of a DC motor. So the software should accept parameters, time, which is the time to run the controller, after which it just stops the motor. T sub S, which is the controller time step, which is that time step parameter we talked about in the discrete control theory lecture. And then Kp, Kd, and Ki, which are the PID constants or coefficients, and the set point, which is the speed that you want it to run at. And so we'll just have one set point. We won't be changing the set point as it runs, although you could do that too. So we're going to just implement this in software, and ultimately the motor is controlled by a pulse width modulation signal, and so we've done that now in the last 2 labs. You can choose whether you want to do a bit banged version where it's controlled by software, or if you want to implement that in hardware like you did in lab 3. I'll leave that up to you. The motor is these things I found on Adafruit. It's just a little standard DC motor, but it has on the back, it has a Hall effect encoder, which is where you sense the magnetic field of the motor shaft. And the motor also has a gearbox on it, and the gearbox reduces the speed of the internal shaft by a factor of 50. It's a 50-to-1 gearbox. So the encoder is measuring the speed of the internal shaft, but we want to control the speed of the external shaft after the gearbox. But that's not difficult to deal with. It's just a constant. We multiply by 50 for the whatever speed, or we divide by 50 rather, whatever speed we're sensing on the internal shaft. Does that make sense? Okay, and then the motor has 6 pins. Now, it used to be you could read what those pins are right there, except unfortunately, now that we've built this little enclosure, you can't actually see that silkscreen layer on that circuit board. But I give you the wires all have different colors, and I give you the color codes. So there's 6 pins on the motor, and the pins are M1 and M2, which are basically how you control the motor. M1 and M2 are just 2 different voltages that control the forwards or backwards speed. So you only want to use one of those at a time. Okay. Now the motor is a 6-volt motor, so if you put 6 volts on it, it'll just run at its maximum speed. But if you put something less than 6 volts, it'll run slower. That's the idea. So M1 is the white wire, and M2 is the red wire. Right, so it's M1 and M2, right? And so those are just the motor power, forward and backward motor power. And then there's a ground connection and a VCC connection, which is just power and ground. And then there's C1 and C2, which are the encoder outputs. And those are, the encoder output is a pulse. And all you have to do is measure the distance between pulses. So you could think of that like almost like a piece, almost like it's like a pulse width modulated signal, except you're just having to calculate the period. And the period of that pulse is the speed of the motor. Make sense? Now, the reason why there's two of them is because you want to be able to detect the directionality, which direction the motor is turning. And so both of those C1 and C2 give you the pulsed output, but you can check the phase of the two to determine which direction it's going. So if you see the rising edge of C1 before the rising edge of C2, it's rotating in one direction, and otherwise it's rotating in the other direction. Make sense? Okay, so that's the way you use that. It's a little tricky to read those encoder outputs, but I have an algorithm for you that shows you how to do that, at least the way that the easiest way I think you can do it. And then the motor, the problem with the motor is that it can't be powered directly from the FPGA board. The FPGA board does give you a power out. There's a VDD and a ground on the ribbon cable connector. But when I tried to use that, I found that it wasn't able to provide enough power for the motor. And that's okay because we have these power supplies in the lab. So you can just use the power supplies. But also, in order to control, in order to basically have the motor M1 and M2 inputs be a value between 0 and 6 volts, that also is able to supply enough current to the motor, we're using this H-bridge chip. This is a small chip that we have in the lab. It has 8 pins. And basically the idea with an H-bridge is that it's comprised of 4 transistors. And then you put the motor in the middle of those 4 transistors. So it's connected to the middle terminal. So you have basically 2 transistors in series, and then those 2 transistors in series are in parallel with another 2 transistors in series. And then the motor is connected to the midpoint between each of the pairs of transistors that are in series. So it forms like an H shape, see? It's like line there, line in the middle, okay? And so the motor then, if you control the 2 transistors that are diagonal with a PWM signal, then what you're doing is you're basically turning on a path of current that comes down here, this leg, and then through the motor and then down this leg, right? But you're also doing it intermittently, or you're switching those using a PWM signal. And so, like for example, if you have a 100% duty cycle and these 2 transistors are connected, then you just get the full 6-volt supply flows through the motor. And if you have a 50% duty cycle, then 50% of the time these guys are on, 50% of the time they're off. And so the effective voltage you'll see in here is 3 volts.
Are we going to be switching the direction of the motor?
Right, that too. So if you then do the same thing with the other pair of transistors, then you get the same effect, but it reverses the flow of the current, right? So that way you can reverse it, right? Now in this lab, the set point is going to be an RPM value, which could be positive or negative, right? I've only tested it personally with the positive voltage, and the positive RPM, the one direction. So if you guys are able to get it to work with that, I'd be fine with just have it run in one direction. But ideally, you'd be able handle either direction. Does that make sense? So you have like 50 RPM or negative 50 RPM, for instance. But so just to clarify here, you're either going to use, you're only going to use one pair of transistors at a time, depending on what direction you want to go to, and then you're going to send a PWM signal. Okay? Does that make sense? So then motor, as I mentioned, the motor has pins called M1 and M2, which are the inputs that you would send current either direction from M1 to M2 to make the motor turn. And then the H bridge, its pins are called OA and OB. And so OA then is going to be connected to M1 and OB is going to be connected to M2. So on the H bridge, you're going to wire OA to M1 and OB to M2. Okay, that's all you have to do. And then the H bridge is then controlled by pins called IA, right, or just IA, right? IA is wired to these two, and IB is wired to these two, right? So the H bridge has an input, IA, or two inputs, IA and IB, and two outputs, OA and OB, right? But the IA and IB are just pulse width modulated signals, PWM signals. It's the same thing that we use to connect to the LEDs, right? Same idea. It's the same way that we brighten the LEDs. Does that make sense? Okay, so okay, so the encoder then, so there's this calculation you can use for the encoder. So we're going to use the performance counter on the FPGA, like we did before, as a clock, pretty much. Like, you know, you're just going to use it as a time reference. And so if you can identify the time between rising edges on the encoder, that's the period, and you can use that period to calculate the speed. So the speed would be 1 divided by the period, because the period is the time between pulses. The encoder will generate 12 pulses in one rotation. So when the internal shaft of the motor rotates once, you're going to get 12 pulses. So when you calculate this period, you're calculating the time it takes for the motor to rotate 1/12 of a revolution. And so if you take that period and you divide it by the gearing ratio, which is 50, and then you divide that by the number of ticks per rotation, which is 12. Those backslashes shouldn't be there. I forgot to take those out when I put this in a code block. So ticks per rotation is just, in this case, is 12. And then you multiply the result of that by 60. That's going to give you the RPM, right? So all you have to do to measure the RPM of the motor is really just to measure the period. And measuring the period requires you to time how long it takes to go from one rising edge to the next of the encoder. Okay? Does that make sense? That's just, it's part of the, it's just a constant 12. Because you get 12 ticks. I guess that's probably not the right term. It's pulses per revolution, not ticks per revolution.
Is that like?
It's just the way that the encoder was built. Yeah, I mean, or you could just use constants. I just use constants in my code. Gearing, I just put 50, and for this, I put 14. Yeah. That makes sense? Now, the question is, how do you calculate the period of a pulse? To do that, you can read the encoder, right, and compare it to what you saw the last time you read it. So if you read the encoder output and it's 1, but the previous time you read it was 0, then you know that you've detected a rising edge. All you have to do is keep track of the current value of the encoder and the previous one, right? That's all you got to do. And also, when every time you find that rising edge, you record the time, the counter value. So the next time you get the rising edge, you get a new counter value, and the difference is just the period, right? Does that make sense? Okay, so that's not, that part isn't too bad. it's a little strange at the beginning because you have to set initial values for all this stuff. But once it gets going, it should give you the that period. And I'm going to fix this. I'll fix that typo when I get back. Okay, so the FPGA board has this GPIO connector on it, and it has 40 pins, I believe, and we just need 4 pins on this thing. We just need 2 pins for the H bridge, right? And as I mentioned, if you just use one of them, I'd be fine with that. But if 2 pins in order to have rotation in either direction, right? So you're going to have 2 PWM pins. Remember, you guys had 26 pins in the last lab, right? You just need 2 now. And then you just need 2 that are inputs. So you can use these pins as inputs or outputs on this connector. And then you'll notice that there's a 5-volt supply and a ground. We're not going to use the 5-volt supply because we're going to use the external power supply. There's also a 3.3-volt supply. We are going to use these ground, though, to create a common ground between the FPGA board and the power supply. So we're going to short the ground from here to the ground on the power supply. That makes sense? So you only need five pins on here in total. Okay, so I have the steps on how to set that up. So all you have to do in your project, in the project from the last lab, you just have to add another port to your lights module, your top level module. And so you can declare that as in-out, because it's input-output, in-out logic 35 down to 0 GPIO. Because there's 36 pins you can use because the other 4, there's 2 power and 2 ground, right? So there's 4 power and ground pins. The rest of the 40 are available for use as GPIO, and you only need to use 4 of those. And then you're going to need a parallel I/O inside your NEOS project, just like you guys did for Lab 2, parallel I/O, like the way that you connected the LEDs. And then you're going to need one for the inputs for the encoder in, and one for the outputs, the PWM out. So it's pretty much the same. The setup there is the same as we did in the past for connecting to having outputs to the inputs and outputs. Or actually, we never had inputs before, but we had the outputs, the LEDs. Now we're just going to add 2 inputs. And then you can connect in the lights. You just have to associate lights.sv. You want to associate the PWM coming out of the NEO system to GPIO 1 down to 0, and the encoder in will be GPIO 3 down to 0. And you don't actually have to use those exact pins. You might want to use different. It doesn't matter which of the 36 pins you use actually for these, as long as you remember what you use so you know what to connect the wires to. Does that make sense? Okay. All right. And then so I have some steps on how to set it up. So this diagram is a little hard to read. I apologize for that. But we have these power supplies in the lab, and they're pretty nice power supplies. They have 3 outputs that you can set up, and the thing has it's a 200 watt power supply, and you can set up 3 different voltages, and then once you set it up, it'll actually tell you how much current is being sourced from that output, and you can limit the current too. So it will protect you in case you have a short circuit. You can limit the current to like 100 milliamps. You won't need any more than 100 milliamps of current. I think by default that's the limit. So just in case you kind of mess up your wiring, this power supply will protect you. It won't allow you to burn anything. So you have to just take the output from one of those 3 outputs. I usually just use the first one and just connect it to your breadboard. Your breadboard has plus and minus rows here for the power. So you can just use that. Now, this picture is a little bit misleading because the breadboards that we have in class or in the lab only have 1 power supply rail, and it's actually at the bottom. It's down here. This is just a generic picture I got from the internet, so try not to be confused by that. But there's just, yeah, there's this one. I don't know why we only have one power supply rail on those ones that we have in the lab, but yeah, it's just, you can just connect the plus to plus side and the ground to the minus side there. And then the ground, you can then connect the ground back to the ground connector on the FPGA, so you'll get a common ground there. So that will short the ground from here to the ground on the FPGA, so they'll both have a common reference. And then you just have to stick the H bridge on there in the middle. And notice, I know this might be hard to see, but notice that there's this like little white half circle on here. That's going to tell you whether you have the H bridge right side up or upside down. That little half circle should be on the left, right? It's a little hard to see. So that's one other thing you want to be careful of. Make sure you have this right side up. So you stick it there on the breadboard, and then you just have to connect. There's two VDDs on there, two power pins that you connect back up to your plus rail here. And there's two grounds that you connect to ground. Okay, and then the outer two pins on the bottom are going to go to your M1 and M2 on the motor. That's IA and IB. And then that's OA and OB rather, OA and OB. And IA and IB are the inputs, and those ones are on the top two middle pins, and those are going to go directly to the FPGA. So that'll allow the FPGA to control IA and IB. And by controlling those, you're controlling the H bridge, and the H bridge is what actually controls the motor. And then as the motor spins, it's going to send the pulses back to the FPGA on the GPIO. Does that make sense? So it's pretty simple to wire up. You may also want to, when I did this, I also stuck an LED here too that blinks just as a sanity check, you know, so I could have it blink while I run the code. Or you could use the LEDs on the board. Does that make sense? So like when you run it, you know it's doing something. It's like a heartbeat, right? Even if the motor's not working. That's up to you though. And then the power supply, it's a little difficult to use. So I put the steps on it here, down here. So you turn on the power supply, you push the green power button. Now when you do that, it's not actually powering the outputs. It's just turning on the power supply. Then you press the channel 1 button, you know, for channel 1, first output. And then you hit the V-set button. And then you type in 6.00 and hit the enter button. Okay? That makes sense, right? The problem is that as soon as you do that, it will then zero out the voltage. It'll make it 0. And so your first thought is, oh, something went wrong. I typed in 6 volts and it rejected that. It reset it, right? But it didn't, because what it's saying to you is that, yes, I know you want 6 volts on channel 1, but because you haven't energized channel 1 yet, I'm just showing 0 volts, right, as the current output state, right? So don't get freaked out when you see it go from 6 back to 0, because when you hit the on button for channel 1, it will then make it 6 volts again after you turn on the channel. Does that make sense? I really don't like that interface. It's confusing, but because like I said, you type in 6 and it kind of just deletes it immediately. But that's just because the channel's not on. Okay? Once you turn it on, then it'll say 6 volts and it'll show you how much current is coming out of that channel. So you'll have an idea of what kind of draw you have, right? And so once the motor starts churning, you'll start to see a current draw. If you tell the motor to go full speed, I think it's about 100 milliamps is full speed. But if you go half speed, it's roughly half that, right? So you'll see the power supply telling you how much current is coming out, which is kind of nice. And if you short it, it'll just stop at 100 milliamps. Okay, so that's described there. Okay, and then, so one of the things that's a little strange here is I did some measurements, and I took the input to the H bridge, the PWM duty cycle. So the duty cycle is between 0 and 1, right? But I also have it go between 0 and -1 if I want to go reverse direction. So if the duty cycle is negative, the code just sends that duty cycle percentage out on one pin. And if it's positive, it sends it on the other. Right? Does that make sense? So technically, my internal value of the power is between 1 and or -1 and 1. Right? You guys following that? Right? So basically, it's just a duty cycle. It's a percentage, percentage that the PWM is on. Right? So if I wrote some code that takes it from 0, it goes up to 1, and then it goes down to -1, and then it goes back to 0, right? And the whole time I do that, I'm also measuring the rotational speed of the motor using the encoder, right? And so you'll notice that, that the motor is pretty much off until you get that PWM to about 0.4. The motor won't even turn until you hit 40% duty cycle, right? Which is like 40% of the 6 volts, right? So it's like 0.6, 2.4 volts. Yeah, 2.4 volts, 2.4 volts. The motor won't even engage until it hits 2.4 volts. But then, from that to about 60% duty cycle, it kind of increases, but then it kind of maxes out at 60%. So if you go from 60% to 100%, it makes like no difference, right? So you have pretty much a useful range there of only about 0.4 to 0.6 on the duty cycle. It's weird, but yeah, that's okay because the controller hopefully will account for that, right? That's and then there's the rotational speed. You'll notice it's a little noisy. And I don't know why that is. I haven't figured this out yet, but I mean, you can expect sensors to have noise. I mean, that's pretty common. This has a lot of noise though. In fact, the encoders seem to almost settle in discrete speeds. You see how the speed sort of varies in discrete? I think though, this may be just because of the way I wrote the code. You guys might be able to do better than I did here, right? I mean, maybe this is an artifact of the software. This isn't necessarily a problem with the encoder, but I don't know. But regardless, the control algorithm hopefully will be able to cope with this as well, right? We'll be able to still reach the set point. Does that make sense? So the set point that we want to use is 1 RPM. That would turn that thing into essentially a second hand that would take 1 minute to go around, right? So it'll kind of make it into a clock, an analog clock is the idea. Does that make sense? Now the motor will spin much faster than that. So in fact, it may be difficult to get it that slow. You may end up having to run a little faster. But we can set the set point, right? The fastest it'll run, according to this, is about 100 RPMs, right? Now that's, again, this is the external shaft speed. The internal shaft is actually running 50 times faster than that, right? But after the gearbox, what you're actually seeing on that second hand is going to be is been translated here. Okay, you guys with me? So that encoder is going really fast. It's a high-speed signal. In fact, now that I think about it, I think I might have just figured out why this happened. Because when I measured this, I was only measuring the encoder, I think, at like 100 RPM, 100 hertz, right? I might have just been measuring that thing too slow. That might have been why we got this discretization. But we want to be able to set that speed as well, the sample rate. That's the sample rate. You guys with me? So yeah, I think that might be why. I might have just been sampling it too slow. Okay, so now you might say, how'd you get that data? You can print. I just put prints. I just logged my measurements in my program, and then I just printed them. And then I took the printed data and I just copied and pasted it into a file and just read it in MATLAB. I also wrote a Python script that'll do the plotting too. I just want to do some debugging or some testing on it, and I'll send that out.
Are we going to be making a plot today?
You don't have to, no. No, this is just for informative. This is just for information. I do want you to log the data for testing purposes, but you don't have to plot it. Just print it to the console. But it's not hard to log it if you have it printed, you know. Just print it as a CSV, and then you can read it into Excel or Python or MATLAB or whatever you want. You can print it. You can log it. Okay. Okay, so the point here, though, is that the blue line is the duty cycle, is the input to the system. You can think of this as the manipulated variable, right? And this orange line is the value from the sensor. This is the process variable, right? So in the controller theory, you've got the process variable here and the manipulated variable here, and you can see basically what the relationship is between the input and what the input to the motor is and what it's actually doing. Okay, okay, so then I gave you guys like basically a pseudocode algorithm for the whole thing. Because I know that we don't have a lot of time. We only have 3 weeks, and you guys are working individually. So now you don't have to follow this exactly. You might find a better way to do it. But the way I did it was I just had a while loop, an infinite while loop. And so I read the cycle counter. The first thing I did is I read the cycle counter, which you guys already have the code that does that. And then the pulse width modulation, I used a frequency of the 50 megahertz. The counter, remember, the counter's at 50 megahertz, right? So I'm basically dividing it by 2 to the 12th power, which is 2048. So I'm basically reducing the counter frequency. The PWM is cycling at 2,048 times slower than the system clock of 50 megahertz, which is about 24 kilohertz. Okay, 50 million divided by 2048 is about 24,000. Okay, that's a pretty typical PWM frequency. You might say, is that ideal? Is that optimal? I don't know. I actually don't know. I don't know how we evaluate that, but it seemed to work well for me. I think that's basically what we used before, right? In the labs, something like that. So the PWM progress, therefore, is just a number between 0 and 2047, which represents the progress of each PWM period, right? Once it goes back to 0, once it rolls back to 0, then we're going to start a new PWM cycle, okay? Make sense? Okay, and then once you have that, then the software can determine the duty cycle. The duty cycle would just be a portion of that 2048, 0 to 2047 value. So the absolute value of the motor input, because remember I said the motor input could be -1 to 1. So if you take the absolute value and you multiply it by 2048, that'll give you the number that you're high, right? And so if that number is less than the duty cycles, darn it. Sorry, there's a typo there too. That should be duty cycles. Sorry. If the PWM progress, which is just a counter that's just dumbly counting between 0 and 2047, if that's less than duty cycles, then you're going to have a 1 coming out, otherwise 0. So that'll give you the PWM signal. And there's a speed. If the speed is less than 0, you're going to use one PWM out. And if it's greater than or equal to 0, you're going to use the other PWM out, that's just the H bridge, the sides of the H bridge. Okay? Make sense? Now, keep in mind though that the PWM progress is not being updated every clock cycle. It's only being updated every time this loop repeats, right? And so the loop might be repeating how many clock cycles it take for that loop to get to the top and read the performance counter. I don't know, but it could be a couple hundred, couple thousand, right? So by doing the PWM in software, it's not as good as a hardware version of the PWM, right? So I think it'd be better to do it in hardware, but at least this way, it's all, you're just writing software mainly. You're limiting the complexity of the design. So I'll leave that up to you, however you want to do it. I have to fix the indents here too, sorry. Okay, and then after that, you read the encoder values, and then the encoder, basically you say if the previous encoder value is 0 and the current encoder value is 1, then that means that you've got a rising edge, you've detected a rising edge, at which point you can calculate the period of the encoder, which is the counter, which is the performance counter that we most recently read, minus the last counter value that we recorded on the last rising edge, and divide that by frequency, and that'll give you the period. That'll give you the time between two consecutive rising edges. And then you update your rising edge time, and that's it. And also, now this is the part that's a little weird. When that happens, when you detect the rising edge, if the other encoder is already 1, then you can assume you're going in one direction. Otherwise, you can assume it's the other direction. That's just because of the way the phases line up for the two pulses. Does that make sense? So in other words, what I'm trying to say here is that when you detect the rising edge, if the other encoder already had its rising edge, if we're lagging behind the other encoder, that means we're going in one direction. But if we're not lagging the other encoder, we're going in the other direction, right? So that's just a way to tell which direction. And then the code is basically copied and pasted here for the other encoder. So we have encoder 0 and encoder 1. Make sense? Because there's two encoder pins. Now you might say, well, wait a minute. I mean, you've got two encoders. They're out of phase, but the periods should be the same, right? I mean, if you know the period of one encoder, why do you need to calculate the period of the other encoder? It doesn't really matter. It doesn't. It actually doesn't. In fact, I don't even know if you need this. I don't know if you need this other block of code. The reason I put it in was because by putting this in, you're getting two opportunities for each period of the encoder to calculate the speed. So basically, this is going to give you a more up-to-date speed, right? You see what I mean? Like, so basically, you can only read the speed of the motor on the rising edge of the encoder output, right? So you might as well recalculate the speed on each rising edge if you have two signals. You might as well do it on both. They're both supposed to be roughly the same, right? But if the motor speed is changing, if the behavior is changing, like if you're really slowing it down fast, by updating the encoder period twice, you're getting a more up-to-date measurement. Does that make sense? So I just basically copied and pasted this twice for the two encoders. But that's not, like I said, I don't think it may not be needed there. And then this calculates the external shaft speed. This is just the equation I gave you before. And then this records the old encoder inputs, basically, so we can detect the edges, right? Just saves the current value. So on the next iteration, we have the old value. And then the final part of the code here detects whether we should perform control. So for this, we have some code here, and the purpose is to enforce the time step. So remember we talked about in discrete control there's a time step, T sub s. This loop, I don't know how fast this loop is. Like I don't know how many times per second we can go through this loop. But I don't think we want to calculate control on every iteration of this loop, right? Every time we go through this loop, we can update the encoder speeds, right? The encoder value. And we can also control the PWM, right? But we don't necessarily want to mess with the controller, the motor input on every trip through the loop, right? So basically this code just calculates how long it's been since the last time we performed any kind of control action, and we wait for that to be at least TS, before we do it, right? That's all it is. So that way, TS allows you to control how fast you want to make control updates. Does that make sense? So, and it's just all based on the cycle counter. So cycles since last control is counter minus previous control action cycles. So this is the current time and the time of the last time we did anything here for the controller. And then you have to divide that by CPU frequency to convert it to seconds from cycles. And then I also keep track of the time since the start. So that way we know when we should stop, right? So this is the counter, right, divided by the frequency. Now remember, the counter starts at 0 when you start your program up because we reset the performance counter. Remember that? There was a thing you put in there to reset it. So I just use the raw counter value to determine how long it's been since we started running the program. And then you perform the control. Well, there's an if statement that checks to see if you hit TS. And then this just does a PID control. And then I mentioned that you should log the time since start, the motor input, and the current motor RPM. When I say log, I mean just record them to an array. And then at the end, you can just print the array out to the console. Okay? And that's it. And I have to fix that indent there too. Any questions? It's pretty long, but it's mostly just checking the clock, checking the performance counter, and doing stuff based on that. Now the problem is that there's an error delta, and an error cum. So error delta is the change in error. The error cum is the accumulated error. Error, of course, is the current motor RPM minus the set point, right? So those are the terms for your PID controller. And then there's the coefficients Kp, Kd, and Ki, proportional, derivative, and integrative terms. You'll have to set these manually, just through trial and error. Does it make sense? And that's it. Any questions about that? So there's a lot of steps, but I think it's like I said, it's the hardware stuff is fairly simple. Although, like I said, it would be better if we did a hardware PWM. And you can, if you want to do that, you can just adapt the design from Lab 3 and include that. Okay. Okay, I'll talk about it. Go over this again in lab on Wednesday, and hopefully we can get that going. We're going to bring. I have a whole batch of these things. I'm going to bring down to the lab, and so we'll have all the parts down there. And they're not down there right now. I'm going to bring them down on Wednesday because I figured out that these wires are not stripped enough to fit them into the breadboard or the wires, the little female wires that we have down there. So I need to wire strip these guys, and I'll bring them down on Wednesday. Okay. Okay, so now I'm going to go ahead and talk about and introduce the next topic, which is real-time scheduling. So you guys probably have you taken 311 yet? Operating systems? Have you already taken it? Okay, so you know that like the operating system schedules processes. It determines which program gets the CPU or CPUs, as in the case of a multi-core CPU, at a time, right? You generally have more processes than you have CPUs, and so the scheduler is going to allow those CPUs, the physical CPUs, to be shared. So the problem is that if we assume that each process is a task, now this is a little confusing because on a regular desktop computer or laptop or a server, you have processes that are kind of just running forever. You know, they're just like background processes. And then you have other things that, you know, like for example, if you're playing like a game or something, you know, you have an interactive process. But if you think of control theory, like we talked about last lecture, where you have a control algorithm that has to run every so often, if you imagine that as a task, right? So you you have these tasks, and as you might imagine, it is often the case that you have multiple controllers running on one CPU, right, or running on a set of CPUs, but the number of tasks you have, or control tasks, may be higher than the number of cores. So you have to have the operating system determine, which of those tasks is getting run on a CPU. Does that make sense? Okay. The problem is that general purpose operating systems like Linux and Windows, they don't allow you to tell it how fast you want each task to execute. Right? It doesn't make any kind of performance guarantees is the problem, right? But if you have a control type system where you have to run each task within an allotted amount of time, which is going to be your TS, your time period, right? Your time step, then you have to have a guarantee that the CPU will be able to keep pace, right? It'll be able to keep up, and that you won't miss any deadlines, right? And so this is what's called real-time scheduling, right? You need to have the CPU keep up with something that's going on in real time, in like the physical world, right? And so that's in that case, you need a real-time operating system. And Linux is not a real-time operating system, neither is Windows. In fact, most real-time operating systems are kind of expensive, right? They're not free. In fact, I don't know of any free ones except for there's one called FreeRTOS. But outside of that one, real-time operating systems are generally kind of specialized, and they're used for control systems. So, so the question is, for real-time scheduling, I mean, is this hard? And when I say hard, it's like if I need to guarantee that I have a set of tasks that I need to have done by a certain deadline on each task, is that a hard problem? And what happens if, for example, I have more tasks than the CPU could possibly run, right? Like, how do I know if it's even feasible to meet deadlines for a set of tasks? And then, like, what algorithms can be used for this, and how do we evaluate them? And how does this apply to cyber physical systems? Well, that's just, it's needed for control. So usually with real-time operating systems, you have a set of tasks, and those tasks are usually some kind of control, closed-loop feedback control algorithm, and each one of them has a deadline, which is just essentially their time step. Now, the problem with this is that CPUs, even if you take a task and you give it a whole CPU and you allow it to run to completion, the amount of time it takes to run it can vary. It usually varies quite a bit. And the reason it varies is because you have these unpredictable things that affect the performance, like interrupts, right? We talked about interrupts at the beginning of this class. So if you have an interrupt occurs, the CPU responds to it by running a service routine for that interrupt and then goes back to what it was doing. But there's also like page faults and cache misses, and there's things that can happen. And that's even assuming that the process or the task always executes the same workload every time it's invoked. Sometimes you may have a task that executes a different workload depending on the inputs. Like there might be like basically an if statement in there, right, that causes it to do more work depending on the inputs. So, like if you have a task and you want to be able to run it in real time, one of the first things you have to do is find its worst case execution time. How long, what is the most time it could take to run? So we have an idea of kind of the worst case of runtime. So, like, for example, if you have a task, you might run it a bunch of times, and you may see, if you plot all those execution times you put them in a distribution and you show it as a histogram, you may see that it's like, it's sometimes you'll see that the execution time distribution is follows a kind of a Gaussian normal distribution. Or sometimes it might be an exponential distribution. But let's just assume that it's a normal Gaussian normal distribution. And so if you calculate you can calculate the mean and the standard deviation. And when you calculate the worst case execution time, what you're basically doing is taking the mean and you're adding standard deviations to that mean. So if you add 2 times 326 times the standard deviation to the mean, that will give you a worst case execution time that is based on a 99% confidence. Or if you take the standard deviation, multiply it by 3.09 and add it to the mean, that'll give you a 99.9% confidence. And 3.719 standard deviations to the mean is a 99.99% confidence. So you're basically coming up with a worst case execution time based on a confidence. And you're hoping that the standard deviation is small, because if it's not small, then your worst case execution time is going to be far above the average execution time. Does that make sense? As I mentioned, like you may find out if you run a task a bunch of times, you may find out that it's, it may actually be a mixture of 2 distributions. So you may have 2 distributions in there that you can each model as a normal distribution with 2 separate means and 2 different standard deviations. Now, why would you see that? Well, this would indicate that if you see this kind of runtime distribution, this would indicate that the software has 2 different amounts of workload that it's doing depending on the input data, right? Depending on some, state, some factor when it runs. And if you see that, that's good, because actually there's 3 different distributions in there. You see how they have these 3 different bell curves here. If you have this, then this actually could improve your estimate, because then you can calculate your worst case execution time based on whatever confidence you want for all 3 of these distributions, and then you just have to pick whatever the highest of those are, right, to be your overall worst case execution time. Now you might say, well, wait, how's that going to be better? Well, it is better. It's a better estimate, because if you do it that way, generally what will happen is the standard deviation of each of those individual distributions will be much less than the one you'd get if you tried to model these all as one distribution, right? So you'll get a better estimate if you can model it better. So here's an example of that. So let's say you measure a task execution time for 10 runs, and you get 12, 13, 10, 14, 11, 30, 27, 25, 31, and 32 milliseconds. And so what's the worst case execution time at 99.9% confidence, assuming a normal distribution? Well, you can just calculate the mean and the standard deviation. The mean is 20.5. The standard deviation is 9.2. And so the worst case execution time is the 20.5 plus 3 times 0.9 times 9.2 is 48.9 milliseconds. But what if you knew that the first and second 5 measurements are generated from 2 separate control paths in the code? And so they're, in that case, you can calculate 2 means and 2 standard deviations, in which case the first one's 12. So the first 5, right? 1, 2, 3, 4, 5. If you take these 5, the average is 12. And if you take the last 5, 1, 2, 3, 4, 5, the average there is 29. And then the standard deviation for the first set is 1.6, and the standard deviation for the second set is 2.9. And so the worst case execution time for the first set is 16.9, and for the second set is 38. So you're going to take the max of those 2 as 38, which is much better than the 48.9 that we measured originally, right? So knowing that we have 2 distributions there allowed us to get a smaller worst case execution time. Okay, so what about the actual scheduling algorithm? So a task, and you probably remember this from 211, right? Processes in an operating system can have states. For example, it could be ready, which means that the task wants to run. It can run, but it's not running because it's having to, yield. There's other tasks that are running that have the CPUs at that moment. A task can be asleep meaning that it's completed execution and it's waiting to be reinvoked, run again, essentially. Or executing, meaning that it's currently on a CPU running. So let's assume that you have 4 tasks, for instance, and you have this says computation time, but this is the worst case execution time, is 40 milliseconds, 6 milliseconds, 14 milliseconds, and 20 milliseconds for the 4 tasks. And then we're going to assume that each of these guys has a deadline. Now, in this case, I'm just going to assume we're just going to run these once, right? Not run them over and over again. So in this case, and if we assume there's only one CPU, so only one of these guys can run at a time, those 4 tasks can be executed in 4 factorial possible orders, right? 4 times 3 times 2 times 1. It's 24 different orders that we can run them in. And it turns out that out of those 24 orders, I think there's only 2 of them where all 4 tasks meet their deadline, right? Now, I'm also assuming, by the way, that every time I run one of these guys, I run it till completion. So to show this, I'm showing it kind of like a timing diagram here, where each task, as time marches on, one task, at most one task can run, meaning that it's high, and the other 3 are going to be low, right? So this means that I'm going to run task 4 first, and when it gets done, I'm going to run task 3 at that point, and when it gets done, I'm going to run task 2, and when it gets done, I'm going to run task 1. So basically, I'm going to run them task 4, 3, 2, and 1. Now, I'm showing the deadlines for each task are these little red lines, and you can see that task 1 missed its deadline because its deadline was at 76 milliseconds, and it exceeded that, right? And task 2, it met its deadline because it ran there, and its deadline was way out here. Task 3 met its deadline, barely, and task 4 met its deadline. But we had one task that didn't meet the deadline. And then in the second one, we have task 4 runs, then task 3, and then task 1, then task 2. And in that case, all 4 meet their deadlines. The third case, we have task 4, task 2, task 3, task 1. And in that case, we have task 1 misses its deadline, and task 3 misses its deadline, right? So I show the full enumeration here, but you can see that they all fail except for 2. So this one works, task 4, 3, 1, and 2, that works. And the other one that works is task 3, task 4, task 1, task 2. And every other, that's the only 2 ones that work out. So the point of this is that you can see that even for this really simple case, it's kind of a hard problem to solve because it turns into a combinatorial problem. You have a lot of different ways to run the tasks, and even with the same tasks on the same CPU, there's the correct order to run the tasks may be hard to find. So as it turns out, there are some rules that you can follow to find the orders. They don't always work though. So like for example, in this case, this is the earliest deadline first, which is where you run the tasks in the order that's determined by the deadline by itself. So if we just forget the computation time here and just look at the deadline, and we see that task 3 has the earliest deadline, followed by task 4, then task 1, then task 2. That was actually number 8, the one that worked. And the least slack first is if you look at the deadline minus the computation time, which is the amount of, slack, the amount of time that the difference between the deadline and the execution time. If you run least slack first, that gives you 4, 3, 1, and 2, which was another one that worked out. Another option is to run the one with the shortest task first, which would be task 2, task 3, task 4, task 1, right? So that would be just based on the execution time, ordered by execution time. So we'll do 2, 3, 4, and 1. But that one, in this case, didn't work. So that's fine, except this is really kind of a contrived example. This is overly simplistic because, like I said, it assumes that there's the tests only run once, right? And so it also assumes that these are non-preemptive, meaning that once you start running it, you have to run it to completion, right? That's also not necessarily something you have to do. So this is a really simple example. The more common situation is to have a periodic scheduling algorithm, which is where the deadline of each task is also its period. It's the amount of time between reissues, right? So whenever a task finishes, it goes to sleep until the beginning of the next execution period, in which case it becomes awake, and then it's either going to be in the running state or the waiting state, right? Until it gets executed, at which point it goes to sleep again, right? So that's the period. So if you have this is what you have to use if you use any kind of a discrete control system, is a periodic scheduler. So if we use the same 4 tasks, we'll assume that instead of deadline, I'm just going to call that period, right? So I don't care if a task executes and finishes early inside of its period. All I care about is that I can run it at least once every period, right? Make sense? Okay. Another thing is that generally we can assume that tasks can interrupt another task. Because if a task is running and another task switches from being asleep to being ready, we can interrupt the current task and make it go from executing to ready. In other words, we can suspend execution time to allow another task to run when it becomes ready. And this is called preemption. So most real-time scheduling algorithms assume that you can preempt, right? Because if you have to let each task finish after it starts, that's overly restrictive. That makes it overly difficult to schedule the tasks. You guys with me? Okay. So yeah, and then so one of the ways you can determine if a schedule is feasible at all is through utilization. So if you add up the ratio between the worst case execution time and the period of all the tasks, that gives you a utilization of the processor. And if that utilization is greater than 100%, you know that there's no algorithm that will schedule. I mean, again, assuming there's one CPU. All right, so if we have one CPU, we can only utilize 100% of that CPU, right? So in this case, if we were to take the 4 tasks I had here earlier, and instead of having a deadline, I made it period. And you calculate the utilization, which is 40 over 76 plus 6 over 84 plus 14 over 35 plus 20 over 37. If you add those up, you get 1.5, which is over 100%. So these guys cannot be scheduled in a periodic scheduler. Now you might say, wait a second, you just said in the first slide that you can schedule them. Yes, because they weren't periodic. They only issued once. Like if you only run them once, and that's the deadline, yes, then you can schedule them. But if they're periodic, now you can't, it's impossible, because what ends up happening is that task 4 let's say we execute task 4 by its deadline, we get another task 4 at 37 milliseconds that we add to the workload, And so because of the periodicity, this is non-feasible if these are periodic tasks. Okay, so there's two main approaches for doing periodic preemptive real-time scheduling. The first I kind of alluded to earlier is earliest deadline first, which is where you schedule each task with the earliest deadline first. Right? Now you might say, well, that's common sense. That's easy. Okay, problem solved, right? Well, no, not exactly. The problem with EDF is it works. It's actually an optimal scheduling algorithm for one CPU, meaning that as long as the utilization is less than or equal to 100%, then this will work, right? And we're done, right? The problem is that the problem is finding what the earliest deadline is. The earliest deadline is constantly changing as time marches forward. Because whenever a new task starts a new period, the earliest deadline can change. So if you have a bunch of tasks, the earliest deadline has to be constantly recalculated. So this is a dynamic scheduling algorithm, meaning that we have to constantly reevaluate where we are and who has the earliest deadline at every moment in time, because the number of tasks that need to run and their deadlines, because tasks only have a deadline when they're ready or executing, but when they're asleep, they don't have a deadline, right? So that's the problem. So this one is generally not feasible to use because you have to recalculate the deadline constantly. Rate monotonic scheduling, on the other hand, is a simpler one where you just schedule the tasks with the shortest period first, right? And so that way, so basically what that means is that in earliest deadline first, the priority of each task is constantly changing, whereas in rate monotonic scheduling, the priority is fixed. Each task has one priority that never changes, and it's just based on the period. Now, however, you have to keep in mind, though, that you still have to account for tasks that are becoming ready at the beginning of their period, right? So, so basically, every time a new task becomes ready, you have to, every time a new task begins a new period, you have to then reevaluate who you're going to schedule based on all the priorities of the ready and executing tasks. And if a task is executing when that happens, and when a new task starts a new period, it might have a higher priority, you may have to interrupt the task that's executing and throw in the one that just became ready. Does that make sense? So both of them require preemption. The only difference between these two is that EDF has the task constantly changing priorities, whereas this guy doesn't. Okay? Okay. So the priority then for earliest deadline first is the priority of task K is basically the deadline, right? But what's the deadline? The deadline is the period minus the current cycle modulo the period. So in other words, you have the period is the, so the idea is that we have to figure out where its deadline is relative to where we are now when it becomes, or where we are currently. So as time marches on, and actually, sorry, this guy is not even, this priority may change even without a new period becoming ready, because you're measuring each task's distance to the end of its current, you're basically measuring the distance to the end of its current period. That's the idea there, right? And you have to keep reevaluating that as time marches on. But let me, I'll pick this up next lecture because we're out of time, and we'll finish this real-time scheduling stuff, and then we'll have I think we'll have enough time for one more topic after this. Okay, we'll see you guys in lab on Wednesday.